Log on, tune in, find out. Another good idea from Cambridge.
He's going to tell us about correlation testing for affine.
Thank you, and thank you for the
opportunity to be here. So this is a joint work with Khaled Khatami from McGill, and in a way it's somehow a way we're viewing some of these results on additive combinatorics from a computer science point of view and trying to understand maybe different questions than the questions that people here are trying to understand, and they have a lot of resemblance. And somehow the motivating framework for this work is the area of property testing. So I'm going to give some examples, but in general, it's about you have some large objects, and you're trying to understand some properties of these large objects, but you're not allowed to view these large objects. You're only allowed to view little small samples of them. And somehow you're trying to take these small samples and try to get some understanding of a global structure. And from a computer science point of view, you can think of those as being very, very fast algorithms. So you have huge data structures that you're trying to understand, maybe the internet or something like that. You definitely don't want to run over all the internet and check something. You want to understand some global properties by some very local samples. So let me give a few examples. So I guess this entire area has started by studying graph properties. So here's an example about three-colorability. So see you're given a graph, a huge graph. And the question is this graph three-colorable? So we know three-colorability is an NP-hard problem, but can we say something approximate? And apparently you can. So if you just want to ask, is this graph approximately three-colorable? And by approximately, I mean maybe you can just delete a small number of the edges, and then this graph will be three-colorable. And it turns out this question is relatively easy to answer, even locally. So here's a local way of doing it. So this was done by Goldach, Goldwasser, and Ron 15 years ago. And they studied a bunch of graph properties. This is just one example. And it's a following very simple test. So you sample a small set of vertices in your graph, and you're just checking is your graph three-colorable on this very small set. And obviously, if your graph is three-colorable, it will be three-colorable on any small set. But the surprising thing is that if it's somewhat far from being three-colorable, that means any three-coloring. So again, if maybe we should define. So three-coloring is just assigning colors to each vertex such that neighbors will have distinct colors. So if your graph is somewhat far from being three-colorable, meaning that any three-coloring will violate an epsilon fraction of the edges, then you can witness this locally. Local samples will tell you that your graph is really not three-colorable, and far from three-colorable. Okay, so that's one example coming from graph properties. Another example, which is more relevant to what I'm going to be talking about, is algebraic properties. So here the algebraic is about functions. So we have functions from fp to the n to fp, and think of p as being maybe a small number or 2, and n as being large. And the question is the f a linear function or not? So again, this is a global property of a function, and you can witness this locally. So right, if you sample xy from a function, and you just evaluate your function on xy and x plus y, and you check whether the necessary condition holds, that f of x plus y is f of x plus f of y, then if the function is linear, then you'll always say, yes, it's true. But if the function is somewhat far from linear, then you'll say, well, there's a good chance I'll detect a contradiction. I'll detect a local contradiction to this global property of being close to linear functions. Okay. So that was done by this very, very early on in the 90s by Blum, Lubin, Rubenfeld. We'll get back more to that later, this algebraic property testing. But I just want to comment that there are related fields which don't exactly look like that, but are in spirit really asking about the relation between local and global phenomena. One of them is about codes and locally testable codes and various local codes. So a code is just some subset of elements in fp to the n, and usually it's a linear subspace. And we say it's a code if any two elements are somewhat far apart, if there is some distance between two distinct elements. And we'll say a code is locally testable if you can locally check if a word that you're given is in the code or somewhat far from the code. So So if a code is a linear code, it's defined by some linear constraints. And you can, let's say, assume all these linear constraints have some short bases. So this is something much stronger than that. It said that if I give you a word which is somewhat far from the code word, I can use these short constraints and really verify that it is somewhat far from the code. So if something is somewhat far from the code, many short constraints will be not satisfied. And somehow these locally testable codes, so they were first studied in the 90s, they form the mathematical core of the PCP theorem that I'll get to in the next slide, which essentially says that you can make proofs locally checked. So you can encode proofs in a way that if your theorem is false, then any attempt proof for this theorem will have many inconsistencies, And but even on this, so there are many questions there, but even on these locally testable codes, we still have some, so we understand them quite a lot, but not completely. So we have some very big open problems there. Can we get them to be optimal codes in various ways? But let's not get into that. Now, as I said, the most complicated example of local structure that we have is a PCP theorem about probabilistic checkable proofs, which essentially, as I said, tells that you can encode theorems and proofs in a way that if a theorem is false, that any proof you attempt to give will have many inconsistencies, so locally you'll be able to detect it. Now, a proof system is just another way of saying some let's say some NP problem. So this theorem has become now into an entire field where we study different NP hard problems. We know they're hard to solve exactly, but can we also show that they're hard to approximate? And it turns out that this measure of locality, which measures how well you can approximate a function, differentiates between different NP problems. So although all NP problems are essentially the same if you try to solve exactly, if you just try to solve them approximately, they're not equivalent anymore. Okay, so that was a very rough introduction to property testing. I will mainly be talking about algebraic properties that will be related to additive combinatorics. So just to set the general framework in the background, so we have a universe of objects. In our case, it will be functions, that will be graphs. A property will be some subset of these objects, and we want to test if a function belongs to this property or is somewhat far from this property. And just so to get an understanding, what do we know today? Which properties of mathematical objects are testable? So for graph properties is relatively well understood, and particularly for dense graphs. So we know today that a graph property is testable for dense graph, if and only if it's hereditary. So it really gives a complete characterization of graph properties. For algebraic properties, we have some partial understanding, and for this less structured object, in particular for hardness of approximation and NP hard problems, it's an entire field. So every problem requires some different techniques. Now, what I want to talk about today is a stronger notion that we call correlation testing, and let me explain it. So property testing, or the examples I've shown, asked, okay, I have some object, I'm trying to understand, does this object have a very strong global structure by local samples? Is it very close to being three-colorable as a graph? Is this function very close to being linear, and so on? And in correlation testing, what we're asking is, can you find some very weak global structure? And the motivating example here is inverse Gareth. I guess it should be theorem now, because at least in finite fields, qualitatively, we understand what's going on. And so there we know that we can test if a function is close to linear or close to a higher degree polynomial by local samples. And we can even test very weak correlation. And the question that we try to study here is, can you get other properties that are also testable this way, other than low degree polynomials? Okay, so that's what we call in correlation testing. So let me now define it a bit more formally, and then I'll start with the example of linearity testing, which is the simplest one to explain, and I'm sure many of you have seen it. So you're given some function from fp to the n to the complex numbers, and you could say, is this, what's okay, the correlation of two functions is just an inner product, and then we say a function has correlation with linear functions if it has some noticeable Fourier coefficient. And which is just measuring its, another way of putting it, we're having this set of characters, we're just measuring the maximal correlation of our function with some character. And so that's a global property. And if you, at least the first time I've seen it, I was surprised that you can witness this global property by a very local average. So we have this, the U2 norm of the function is just the average of the function over 4 linear forms. So we just have some variables and we evaluate the function on some linear combination of these variables. And this very local average just looks on 4 values of the function and look on some average, tells us something about the global nature of this function. Okay, so we know, and using Fourier analysis it's easy to see it, that if the function has some noticeable Fourier coefficient, at least epsilon, then this local average will also be noticeable, also at least epsilon. And if the function has no global structure, if let's say if its maximal coefficient is at most delta, where delta is much smaller than epsilon squared, then its U2 norm will also be very small. So one way to view it is that this local average on 4 values of the function allows us to differentiate function which has some correlation with linear functions, epsilon, from functions that have no correlation, have negligible correlation with linear functions. And if you look on the same thing, discrete setting, then we are having some now a function from fp to zen to fp instead of a complex function. And an equivalent way to view it is say, well, we have the following test. So we're just evaluating this discrete function at 4 locations, and they're chosen so that the sum is 0. And this is a very local test, and its acceptance probability, the probability it accepts a function, depends on the correlation this function has with linear functions. It's a set of linear functions. So if the function has some correlation with linear functions, that the probability, so 1 over p is the probability to accept a random function. That's a trivial acceptance probability. And the probability to accept a function that has some correlation is somewhat better than that. So the acceptance probability of this local test, which is equivalent to this linear average that we had before, tells us something about the global nature of this function. Okay, so this is just, I want to set the framework in this relatively simple example of linearity testing. So just to stress one point, is there is another subtle difference here from the area of property testing. Well, in property testing, if you want to check, let's say if a graph is 3-colorable or somewhat far from 3-colorable, we allow the number of queries to increase as the distance became smaller. Here what we have is a stronger property. So we have this test which is fixed. We may repeat it many times if we want to amplify it, but even this fixed test tells us something about the global nature of this function. Okay. And now you can view the inverse Gauss theorem for finite fields as an analog for that for studying correlation with higher degree polynomials. And it essentially tells us that we can witness correlation, which is a more complicated set of objects, also by local averages. So let me define in general this U of a set just being the maximal correlation of a function with a set. So here, poly D is a set of all degree D polynomials. And the question is, and so the maximal correlation of a function with degree D polynomials, just denote this norm U of poly D. And just from technical point of view, we don't really look on polynomials, we're looking on the complex function associated with this polynomial. So the omega, the pth root of unity raised to the power of the polynomial. So but that's the natural way of defining the correlation here. And the Gauss norm is this average on a small set of points on 2 to the d plus 1 points. And the very surprising phenomena is that you can use it to really check correlation with degree D polynomials. Well, at least if the fields are not too small. If the field is small, then you need to look on non-classical polynomials, but in this talk I'll only be talking about large enough fields, so we can ignore this issue. So the direct theorem proved by Gauss says that if the function has some global structure, weak global structure, if it's correlated with degree D polynomials, then the D plus 1 uniformity norm is noticeable. And the inverse theorem, which is much harder, tells us that this local average, this D plus 1 uniformity norm, really does measure some notion of correlation with degree D polynomials, although the parameters decay very badly. But we know that for every, if the D plus 1 uniformity norm is at least epsilon, then there is some noticeable correlation with degree D polynomials. And somehow the main thing that we try to study is, can you generalize this to other things? And the answer is no. Okay, so can you find other properties of functions that these local averages will be able to measure correlation with these other properties? And we'll be looking, and because we really want to study local averages, so things that look like you evaluate your function on x, x plus y, x plus z, and so on, it tells us that our properties should also be invariant under linear transformation. Actually, will require slightly more. Will require them to be invariant under affine transformations. Just to get this linear forms, I'll be talking more about later. And another caveat here that we really be working on finite fields. So when we enlarge enough finite fields, so we can use the inverse theorems to talk about polynomials, not about non-classical polynomials. But okay. So just from a high-level point of view, we're saying that the only properties that you can test by these local averages are essentially low-degree polynomials. But there are other properties which are affine invariant, but they are not testable in that sense. So let me define things a bit more carefully now. So a property, as I said, is just some subset of functions. So in the first half of what I'm going to talk about now, I'm going to be talking about discrete functions, so it'll be somewhat easier to define everything there. You can also study the same questions about complex functions. So again, as we said, the correlation of a function with a property is just a norm associated with this function. It's a maximal correlation of a function with some object, some function that has this property. So if this property is linear functions, this says what's the maximum correlation you have with some linear function. And so what is a local test? So a local test is just some way of looking on a small sample of points in your function and understanding something from it. So here, so a test is just so you have some distribution over, let's say, q points. So q stands for the number of queries you make to your function. And we have some test. So a test is just you evaluate your function on this set of points, and you either say yes or you say no. So let's say yes is 1 and no is 0. Either my function has some local property or not. And you look at some average. And we will say that this test correlation with a property, if intuitively this test allows us to distinguish functions that have some correlation with this property from functions that have no correlation with this property. And to put it more quantitatively, so for every correlation epsilon that you want to detect, there is a much lower correlation delta, which think of it as being almost 0, and such that our test, if the function has correlation, at least epsilon, then this test accepts with some probability, delta plus, at least. And if the function has no correlation, if its correlation is below some delta, which is much lower than epsilon, then this test really accepts with probability which is significantly lower, theta minus. So somehow the acceptance probability of this test tells us whether our function has some correlation or no correlation. Obviously, if you really want to get a very good detection probability, you can then amplify this test, run it many times. But here we are asking that even this very local test will tell us already something about the correlation of the function. So now let me try. So as I said, we'll be studying affine invariant properties, and the whole reason we're doing it is because we really want to say that these local tests are really these local averages. So we can use all the theories that we know about local averages. But just to, so a property, as I said, is just some sort of function, and it's affine invariant if a function belongs to a property, if and only if applying some affine transformation on its inputs will also be the property. So here, so one example is obviously linear functions or degree-D polynomials, right? If you have a degree-D polynomial and I apply some invertible affine transformation on the variables, it will still be a degree-D polynomial. But there are other functions. So that's the algebraic examples. There are more combinatorial examples. So one example is a set of functions that have low dimension or sparse Fourier representation. So if a function could be represented as a sum of 10 Fourier coefficients, then applying some linear transformation or an affine transformation will still get it to be a function of 10 Fourier coefficients. Or in general, if you take any thing here and you try to compose it, so here, so said, and this will also be affine invariant. So you can have these very algebraic examples or these much more, I guess, combinatorial examples of things which are affine invariant. And also, so, as I said, the inverse Gowers theorems can be seen as a way of testing whether a function has correlation with the greedy polynomials, and actually much easier theorems tells you that you can test if you're very close to being a greedy polynomial. And actually you can do the same thing for these other examples. So if you want to check if a function has a low dimension or a sparse Fourier representation, you can also do that. If it has exactly that, or it's somewhat far from that. So for property testing, all these things look roughly the same. You can test if something has very strong property which is affine invariant. And some of the question is, can we test also weak correlation with such functions? So for example, can you test if your function has correlation with some other function that has sparse Fourier representation? It's a legitimate question. And we don't know how to do it with linear averages because we don't have the analogs of the inverse theorems. And essentially what we show is that you really cannot do it. So in a way, the Gauss uniformity norms and the tests that they generate really classify this type of test that you can make to check correlation with any property. So, okay, so again, so let's define this. What are these local averages we want to talk about? So we have some set of variables, and the linear form is just some linear combination of them, and then a set of linear forms which defines an average is just some collection of linear forms. So for example, the one that we had for the linearity test, we just evaluated the function on x plus y plus z, x plus y, x plus z, and x. So 4 points which have some linear relations between them. And then an average, so here we are having functions from fp to the n to the fp, so we're looking on some averages and we may have some coefficients here multiplying them. If you're looking on complex functions, you may have some conjugations, it doesn't matter. You're just averaging your function over some set of linear forms. Okay, so some notion of a generalization of those linear averages that you get in the linearity testing and the Gauss inverse theorems. And essentially what I wanted to say is the reason we're looking on affine invariant properties is because these linear averages really allows us to, any local test can be put as some linear average. So actually the way that you need to look at, if you want to do it carefully, then you don't really just need to take one average, but a small set of averages, and this small set of averages will tell me if my function has correlation or has no correlation with a property. So that's a generalization of having just one average. So you might have several averages, and so for each function I'm evaluating it over several local averages. I'm getting a bunch of numbers, and this bunch of numbers tells me does my function has correlation with a property or not. So one way to put it formally is that if I look on the set of all these numbers that I get for all the functions that have some correlation, in the set of all these numbers, when my function has no correlation, so they are somewhat far apart. Right? So this set of numbers really allows me to tell whether my function has correlation with a property or has no correlation with a property. Okay, so it's not a really crucial point, it's just something technical that you need to handle if you want to really say that any local test can be put as local averages. So if you really want to do it, then you need to allow more than just one local average. You need to allow a set of them. But that's not a very interesting fact. And also, you can also say because our tests are affine invariant, and then you don't have any set of linear averages. You get some specific sets which are homogeneous. So they have these specific forms. It will actually be somewhat important for the technical part of the proof, but it's not very important for the high-level ideas. And just what I said is that any local test can be put as local averages, so it's very simple. So if you have some affine invariant property, it means that doing some affine invariant transformation, so some affine transformation on the input leaves the property invariant. So you could just take any function and apply some affine invariant transformation on its inputs. It will have the same correlation with the property, right? Because the property is affine invariant. So if we just take a uniform affine invariant transformation, uniform affine transformation, this will just transform any query that may come from any distribution to a distribution over linear forms. Because any specific query, let's say x1 to xq, that I will query the function, now becomes this linear form. So somehow the whole point of that is just to say, to justify why it's enough to study linear forms and not general tests that may look bizarre. So I guess if you're not interested in testing, but you're interested in linear forms, and then you can ignore that. So here's the main theorem. So as I said, informally it says that essentially the only properties you can test are the greedy polynomials. And so what we have is the following. So you take any set of properties, or any set of subsets of functions. So we need some constraints on them. So one, they need to be consistent, so that it won't have, so the way they're defined for various values of n should have some consistency between them. So that makes sense. As I said, affine invariant, and for some technical reasons, we also need to be sparse. So we don't want to have a set of all functions being a property. So we want properties to really look like the greedy polynomials, or a relatively small set of functions, not all functions. Okay. And the theorem said that if this property can be locally testable with Q queries, and we want the field to be large enough, so you won't have to handle these non-classical polynomials, then there is some degree, with a small number of queries, that essentially a set of functions which have no bias. So we also want, for some technical reason, we want the function to won't be correlated with constant functions. So we're just looking on unbiased functions. So if you have any unbiased function which has some correlation with our property, then it will have some correlation with degree d-1 polynomials, and vice versa. So really the norm that this property defines is equivalent to the norm defined by the UD uniformity norm. So that's true for any property. So if a property can be locally testable by local averages, then it's equivalent to some uniformity norm, the norm it uses. So this was for the discrete setting where our functions was from fp to the n to fp. You can also have analog results for the complex settings. So a property here will require it to be a set of bounded functions. And it's the same thing. So if this property can be testable by a set of linear averages, then really, let's say if you think of it as a pseudo-randomness, so the way it differentiates a function from its average, if and only if some uniformity norm differentiates a function from its average. So if you think of those as some set of ways of measuring pseudo-randomness, then they are just equivalent to the uniformity norm. You can't get any other norms. So actually a question that I'm interested in is this true for any norm? So is it true that any norm that you define on, let's say, function from fp to the n to c, which is defined by these local averages, is equivalent to some uniformity norm? So this almost tells you that, except that if you allowed properties with unbounded function, it would be really equivalent. But we actually need in our proofs to get it to only handle bounded functions, but maybe the other way around it. So really, I think it would be interesting if you can say that any function, any norm defined by local averages is really equivalent to some uniformity norm. Now, we really don't understand what, if you have a local average either in the additive setting or in the graph setting, we really don't understand when it defines a norm. We don't understand when it's always, let's say, when it's always non-negative even. So this would be interesting if we can't understand it, but we can still say that whenever it is a norm, it's equivalent to some uniformity norm. But that still requires some work. So what we have here doesn't give us that still. Only norms defined by some bounded functions, the correlation with bounded functions. So now let me get to the proof, and I will just describe the proof actually for the complex setting because it's somewhat easier to state here. So again, what we want to show is that if you're given any property that is testable by a set of linear forms, then essentially the norm correlation this property induces is equivalent to some uniformity norm. Okay, so that's what I want to show, and I'll highlight the proof ideas. So here is the main idea. So we're going to define this set S. So let me explain it. So we're looking on the set of all degrees such that I can find polynomials with this degree that on one hand have some correlation with a property, but on the other hand look random enough. And look random enough will be of having some high enough rank, so I'll define this in a bit, but a rank is just, you can think of it as a polynomial has high rank if you can just write it as a function of a small number of lower degree polynomials. So she's equivalent of having no correlation with lower degree polynomials. So really, to think about that, I can find random looking polynomials of more and more variables, and all of them has some correlation with our property. And this set of correlation has some uniform lower bound. Okay, so that's some definition. And one thing which is relatively easy to see that, well, this set cannot be infinite. So you can't have polynomials of arbitrarily large degree that you still have correlation with your property. And the reason is because these local averages, at some point, will not be able to distinguish polynomials of very high degree from the zero function. They will all have average about zero if these polynomials are high rank. So it's actually relatively easy to say that there is some bound here. So let capital D be this maximal number. So a priori, it's not even clear that this set is consecutive. There maybe this capital D is 5, so I can find polynomials of high rank of degree 5 which have correlation, but maybe I cannot find for degree 4. So maybe there are some jumps there. Actually, that will be an issue that we'll have to handle. But let's just look on capital D as being the maximal degrees I can find. And essentially what we'll show is that this capital D classifies the correlation this property induces. So the first lemma, which will be the easier part, will say that if a function has no correlation with degree d plus 1 polynomials, sorry, it has small ud plus 1 norm, so it has no correlation with any of these polynomials, then it really has no correlation with our property. That's going to be the easier case. The harder case is going to show that if a function has no correlation with our property, it has no correlation with any set of polynomials of degree at most d. So somehow, even polynomials that somehow don't come from this definition, some other polynomials. So that's going to be the harder case. But before I'm going to talk about the proof, I'm just going to give some definitions that are standard. So, but if you don't know this area, then they may not be standard. So the rank of a polynomial, as I said, is just the minimal number of polynomials of lower degree you need to write it. And it's just some measure of a pseudo-randomness of this polynomial. So think of polynomials being random if you cannot just write it as a function of a small number of lower degree polynomials. And something which is important to note, that's a theorem of Ben Green and Terry Tau for large fields, and by Tali Kaufman and myself for small fields, is that if a polynomial really has high rank, then it really is equivalent of having no correlation with lower degree polynomials. So having no structure and having no correlation are really qualitatively equivalent. So you can really think about this as being some measure of pseudo-randomness of a polynomial, having high rank. So similarly, you can think of matrices of high rank or quadratic polynomials having high rank as really have no correlation with linear functions. So this is really the analog of that for higher degree polynomials. Okay, a polynomial factor is just a set of polynomials. And we really think of it as given a partition of the input space. So if you have a set of polynomials, we just partition the inputs as whichever values they give on these polynomials. Let's say if we have one polynomial, then we just partition the inputs, all the inputs where the value is to 0, all the inputs where the value is to 1, and so on. And if we have a bunch of polynomials, we're just partitioning the input, in this case, to p to the power c at most, p to the power c boxes. So this really induces some sigma algebra on fp to the n. And we can look on the average of a function on this thing. So if I give you any function from fp to the n to c, you can just, and some polynomial factors, and something that we need is the average of this function of this polynomial factor. It just means that, so again, so if we have some polynomial factor, it induces sets. So let's say one set will be something like all the x's, where q1x is 0, q2x is 1. So that's some partition. And the average of a function, so the average of a function on the polynomial factor will just say for each such cell, I'm just looking on the average of the function in this cell. So this is also be measurable. So just the average in each cell. And some definitions of the complexity of a polynomial factor is just a number of polynomials you need to write in the bases here. Just see. The degree is just a maximal degree of a polynomial appearing here. And the rank is just another way of saying this polynomial factor looks random enough. So formally, it's the minimal rank of some linear combination of these polynomials. But you should think of a polynomial factor having high rank as being saying that all these polynomials are more or less independent. So if I look on a uniform input, x, and I look on what it evaluates on q1 up to qc, then those are uniform, so those are independent variables, more or less. So they have no correlation between the different polynomials. So just some notion of pseudo-randomness. Okay, then another ingredient is decomposition theorems, and it says that if I give you any function, then I can decompose it as a structure part plus a pseudo-random part. And the pseudo-random part is, by the inverse Gauss theorem, tells you that it has low d+1 uniformity norm. The structure part is an average on some polynomial factor of degree d, and high rank and bounded complexity. So just you can fix d, whichever way you'd like, and then the pseudo-randomness will tell you that this f2 part has no correlation with degree d polynomials. This f1 part will just be a function on a small number of polynomials. Okay, so just a standard way of doing decompositions. And then the last thing I need for the from this polynomial definitions is the complexity of linear systems. So again, we have a linear form, and a linear system is just a collection of linear forms, and an average is some average of here I'm multiplying the function on some linear forms, because now it's a complex function. And you may have conjugates, so it's fine. So, but for the simplicity of this presentation, I didn't write the conjugates, but you may have some conjugates as well. So this really looks like something that generalizes the general structure of the inverse Gauss, of the Gauss uniformity norms. And then the complexity is just, well, it's a minimal degree such that these averages cannot distinguish things that look pseudo-random in the d+1 uniformity norm. So if you can decompose your function as f1 plus f2, all bounded, let's say, and f2 has low d+1 uniformity norm, then really f and f1 looks the same to your average. So this average cannot distinguish functions that are difference is small in the d+1 uniformity norm. So you can ask what is the complexity of a given linear system. So there are two answers here. So Green and Tau gave a bound that's called the Cauchy-Schwarz complexity, which says what's the minimal d that you can prove it using Cauchy-Schwarz, essentially. So it gives some bound on d such that this happens. And then Gowers and Wolf asked, okay, but what is the minimal d that you can get it? So the Cauchy-Schwarz gives some bound, sometimes it's not the optimal bound. What is the minimal one? And they gave a very combinatorial characterization of really what is a minimal d, and they proved that this really holds when f1 is a constant function. And in an earlier work with Hamed Khatami, we showed that this also holds if f1 is any function. So it doesn't have to be a constant function. So you can really use these decompositions to study linear forms. So essentially, this tells you that if you're studying your functions on linear forms on your functions, then you can replace any function by a structure function. So the combination of that and the decomposition theorems. We know we can always decompose a function into a structure part and a pseudo-random part, and these averages really don't fill the pseudo-random part. So we really can assume everything is structured, and that's useful. So now let me get back to the proof once I had put the definitions in place. So again, that's what we want to show. So let me just recall what we had. So we had this set S of all degrees, that you can find polynomials of the specific degree of high rank, but still have correlation with no property. Capital D was the maximal value in this set. So this set, again, might not be of consecutive numbers, but takes a maximal number. And there is a maximal number because there is some complexity to linear systems. And then there are two lemmas that we want to show. The easier one is if a function has low d+1 uniformity, no, it has no correlation with a property. And the other one, which is somewhat harder, is that if the function has no correlation with properties, then it really has no correlation with any polynomial of degree at most d. So it has low d+1 uniformity norm. So let's start with the first lemma. So again, capital T is this maximal degree. And let's assume by contradiction that you can find some function, some bounded function, that has low d+1 uniformity norm, but it has some correlation with our property. And the main idea will be that since the linear forms that define this property cannot distinguish such functions from zero, then this cannot happen. That's the main idea. So the first step, as I said, is you can always reduce this question to studying structure functions. So you can always replace f by its average on some polynomial factor of some large degree S, so S may be much larger than this degree D that we're defining with the property, but it's at least some bound that depends just on these linear forms. And we can just replace our function with the function f1, which is the average of f on this polynomial factor. The function now, without loss of generality, will be defined by some function of some degree polynomials, some degree S polynomials. Right, so because linear averages that defined our property cannot distinguish our function from the structured part, then really we can say that our structured part also has some correlation to the property, and also it's easy to show that it also have low D+1 uniformity norms. So the whole goal here was just to reduce from general functions to structured functions. Okay, so we still haven't done much. So we have some structured function that has low correlation. Sorry, that has some correlation to the property but has low D+1 uniformity norm. And we want to show that this cannot really happen. It really if it has low D+1 uniformity norms, then really it should have no correlation with our property. And that's relatively easy. So now we can just use the fact that the function is structured. So if the function is structured, then we can write it as some combination of low degree polynomials. Here, low degree being degree S, so some degree, maybe much larger than D. Right, so we can just write it similar to the Fourier decomposition. Let's decompose this function as some combination of phase function of degree at most S. But now we can combine the two assumptions that we have. Well, I want to show that essentially all these functions have no correlation with the property, so my function also have no correlation with the property. Right, so if those were polynomials of low degree, then because they, by definition, so by assumption, our function has low D+1 uniformity norms, it takes some work, but you can show that also that these coefficients must be 0. Because if these coefficients were not 0, our function would have to have some correlation with D+1. Sorry, have some correlation with degree D polynomials. Okay, so in essentially, assume that all these polynomials are random enough. Fine. Okay, so because our function has no correlation with degree D polynomials, really there cannot be any polynomials of degree at most D appearing here, which has some noticeable coefficient. So this tells that with all the polynomials there must be of degree D+1 and higher. Okay, so but then we know that these polynomials have no correlation with the property, so they also have contribute nothing to the correlation of the function with the property. So really here, this was just, as I said, that's the easier direction. Really it's said that if D+1 uniformity norms bound all these linear, if they bound correlation with the properties, then really having low D+1 uniformity norm meaning that you have no correlation with the property. Okay, so now the more interesting case is the other direction. So you assume that you have no correlation with the property, and you want to show that you have no D+1 uniformity norms. And the key ingredient here is an invariance principle that says the following thing: that if I give you some average over some polynomials, high rank, I can replace these polynomials by any other polynomials, and this average will not notice the difference. The only thing that this average notices is the degree of the polynomials, not the polynomials themselves. So just to put it more formally, so if you take any two collections of polynomials of some degree, all these collections, both collections are of high rank, so they look random enough, and I just force the degrees of Q1 and Q1 prime to be the same with Q2 and Q2 prime to be the same, and so on. So just the degrees are the same. And I'm looking on any function gamma that composes into one function, and now I'm composing two functions, f and f prime. So f is going to be gamma applied to Q1 up to QC. F prime is going to be the same composition function gamma applied to some other bunch of polynomials, just that have the same degree. Then what you can show is that local averages really cannot distinguish f from f prime. So really, the only parameter that's important is the degree of these polynomials, and nothing else. Actually, you need some slight technical condition to really verify that. So one of them is that polynomials are homogeneous. Another one is that the linear averages here are homogeneous, but those are some technical terms. So, but in most cases, this could be said. In particular, in the case of Eustein, this could be said. So really, local averages cannot distinguish functions of polynomials from other ones if the polynomials all have the same degree. So the degrees are the only important parameter. So how can we use it? So the main idea here is that we can, right? So we said there is some polynomial that's correlated with a property. The main idea is that we can use this to show that we can replace it by any other polynomial, and essentially you'll have it will look the same to all these linear averages. So, okay, so again, so we assume by contradiction that we have some function with no correlation with the property, but with some d+1 uniformity norm bounded by some epsilon, and that's before we can reduce f to be in some structured function of polynomials of degree s, where s is some large number, much larger than d. And, well, we assume f1 has correlation with degree d polynomials, so we can find some high rank polynomial that's correlated with f. And in general, we can find it be of some degree, which is at most d, because f has some noticeable d+1 uniformity norm. And let's assume for now it has degree exactly d. It actually will be an easier case. Let's say it has degree exactly d, and it has high rank. Now, by the definition of this set S and this degree d, we can find another polynomial, q prime, might be totally unrelated, but of exactly the same degree, that is correlated with some function in our property. Okay? So we have the following thing. We have our function is correlated with some degree d polynomial, and some function in the property is correlated with some other degree d polynomial. And somehow what we want to say is that because linear averages cannot distinguish something that depends on polynomials, just look on the degree, that time we can replace them. And the way we do it is we're going to define another function, f1 prime, which is essentially going to look on f1, it's going to take its structure, you're going to replace q by q prime, you're going to replace all the other polynomials by some random looking polynomials. And we're going to say that, well, on the one hand, these local averages cannot distinguish f1 from f1 prime, because we kept the degrees the same and we kept everything high rank. So if f1 had no correlation with the property, f1 prime also should have no correlation with the property. But by the way we constructed it, we just plugged this polynomial q prime into f1 prime, so by construction, f1 prime has some correlation with the property. Okay, so that's the main idea here. You can just replace one polynomial by another polynomial and keep all these local averages looking the same. And because they define the property, then also keep the correlation with the property the same. Okay. So just this last part, which turns to be somewhat annoying, is that, okay, what happens if this polynomial f1 prime is correlated with some high rank polynomial, but its degree is lower than d? So we said that the way we define this set S, it's a set of degrees. Capital D was the maximal degree, but there might be some holes in the middle. So actually, we need to show that there are no holes in the middle. So if you can find one high rank polynomial of degree D, which is correlated with the property, you can actually push it down to get polynomials of lower degrees, which are still high rank. Now, that may be problematic because there is no easy way of taking a high rank polynomial of degree D and making it a high rank polynomial of lower degree. The only way is if you can say something that the number of variables is small, is constant, right? Then it's actually a function of linear functions. So actually that's what we need here. So we need the following thing. It's about linear averages. It says the following thing, that if I give you any bunch of local averages and I evaluate them on some bounded functions, then I can always find some fixed n, some constant n, such as this set has some interior. So you can take anything and move it slightly and still be fine. And actually that's a crucial point in pushing these polynomials to be of lower degree. And okay, there are some trivial obstructions where this cannot happen, where this doesn't have non-empty interior. For example, if two linear forms are the same, right? Then let's say if the first and the second one are always the same, then the first two values are always the same. This doesn't have a non-empty interior. But it turns out if you can remove trivial reasons why this cannot happen, then this always has an empty interior. And this is really an analog of a similar theorem of Erdős, Lovász, and Spencer. So they study graph averages. So you look at large graphs and you're counting subgraphs inside them. And they're showing similar things. If you're looking on subgraph counting in large graphs, you can find large enough graphs, or actually, that these things already become to have some interior. And you just adapt the techniques into this additive setting. So just to summarize, so what I discussed in the beginning of the talk, property testing, we said that we can witness very strong structure of functions by some local samples. And what we studied here is, can we witness very weak structure by local samples? So there are many cases where we can witness strong structure, but as it turns out, at least in the algebraic setting, where we're looking at these linear forms, there are not that many. So if you want to witness weak structure, then essentially The only thing you can do is use the inverse Gauss theorems and witness correlation with the greedy polynomials. You cannot find other properties that have this correlation testing. And just a few open problems. So one is about normed spaces. It's about, can you show that any norm defined by local averages is equivalent to some uniformity norm? The other one is really more about testing. So it's really about what happens in local characteristics where the inverse Gauss theorem fails. So we know it tests something, but now it's not polynomials anymore. It's about non-classical polynomials. So here's one example. And I'm trying to spread it to the people, because I think it's a very interesting problem, but we really don't, the tools that we have today are not sufficient to answer it. So we want to test the following simple thing. So we have a Boolean function, so a function from f2 to the n to f2. And the question is it correlated with cubic polynomials? So can I find some cubic Boolean polynomial that has correlation with it? And we know that the U4 norm that tests correlation with cubic non-classical polynomials doesn't work, because the class that it tests correlation with is larger than the class of cubic polynomials. Right? So for example, we have examples of functions that have large U4 norm, but are not correlated with any classic cubic polynomials. But so the question is, can we do it by some other way? And here I'm not asking about correlation testing. I'm asking about this old question about property testing. So I want to distinguish, does my function have at least some correlation epsilon from 0? But I'm allowing the number of queries to depend on epsilon. So I don't really care about having this very local sample that's constant size. So fix epsilon, I want to find some test that distinguishes function which has epsilon correlation with cubic polynomials from functions that have no correlation. So some of the tools that we have today are not sufficient for that. Okay, thank you.
Questions? So can you just repeat what you said at the end there? Are you interested in correlation with cubic polynomials? We're talking sort of 99% correlated.
No, so 99% is fine.
So how do you do that?
Because whenever you can do local correction, so if you're almost a cubic polynomial, you can correct yourself to be in a local cubic polynomial by looking on the averages you get and just correcting it. But if it's not 99%, if you reduce it 99% to a low enough constant, then these things doesn't work anymore. And then but this is much weaker than asking for correlation. So the question is, I guess, right? So you have some function from f2 to the n to f2, and I'm fixing epsilon, and I want to distinguish two cases where f has correlation epsilon with cubics, and the case that has no correlation. And I'm allowing you to use as many queries as you want, but just depend on epsilon. So I don't want to depend on the number of variables.
But if you use the U4 norm first, then that will tell you that either you correlate with a cubic or you correlate with kind of a fake cubic.
Yeah.
We sort of understand what those are.
Yeah.
But you don't know how to distinguish fake cubics from real ones.
Not that, no. Because it really has a very weak correlation with fake cubics.
Well, if there are no further questions, I think Martin Kasabov is giving a lecture in the algebra seminar in like 5 minutes' time. I can't remember what it's on, but might well be interesting. But let's thank Shachar again for this talk.